Okay folks, this is our last pre-work video, and in this example what we're going to learn how to do is to construct the potential function based upon the given gradient field. So here we're told that our vector field f is a conservative vector field, and then we're asked to find the potential function phi of xy. So I'm not going to formally outline the steps for doing this. We're just going to do it by way of an example, and then when we get to class we'll list those steps out a little more carefully. So the first thing I'm going to do is I'm going to go ahead and say that our phi of xy needs to be equal to the integral of f of xy dx. And why is that? Well, here's our component function, f of xy, and that is phi of x. And so if I want to somehow try to get back to the original function phi, and I know that f, that first coordinate function, comes from having taken the first partial of phi with respect to the variable x, then by integrating f with respect to the variable x, that will get me a long ways towards reconstructing my function phi. So let's go ahead and do that then. So we're going to take the integral of 3 plus 2xy dx, and then since my variable y here is being treated as a constant, we'll just go ahead and integrate this the way we normally do. And so when I do that, I end up with 3x plus x squared y, and then normally what we write is plus c, and this is where this differs from the type of integration we've done before. This c, as you recall, stood for an arbitrary constant. So let me just put that. This is usually an arbitrary constant. But because our original function was a multivariable function, and it's been written in terms of both x and y, what we don't know is whether or not that arbitrary constant is a standalone constant, as in a real number, or some expression that had no x's in it. And in that case, it would have been a function of y. So I'm going to go ahead and erase this, and instead of putting c there, I'm going to write c sub y. And so what we're going to think of this is some unknown function, some arbitrary function of y, and we see by writing it that way, it is certainly a constant as far as x is concerned. That is, you don't need to do this, but you could check. If you took phi of x, if you took the partial derivative of this with respect to x, you would end up with 3 plus 2xy, and then because this function, even though it's an arbitrary function, it doesn't depend on x, so when we take its derivative with respect to x, we end up with a 0 there, giving us the original integrand. So the new material here is to, instead of saying we get an arbitrary constant, is to say we get an arbitrary function that does not depend upon x. In this case, because there's only one other variable, it must depend upon y. So that's not all the way done. Just like when you take a normal antiderivative, you're not done when you've still got an arbitrary constant. We're not done finding our original phi of xy because we've got this arbitrary unknown function c of y in there. So what we're claiming is that our phi of xy should look like, let me just summarize that, it should look like 3x plus x squared y plus c sub y. But we know that that's not quite the whole story because we don't know what that function is in terms of y. And so what we can now do is we're going to sort of back step. So one way to look at this is we've got some phi of xy that we're trying to find, and we started off by saying we know that f is equal to phi of x. We also know that g is equal to phi of y. And so we've gotten part of the information by integrating this way. And now what we're going to do is we're going to take the partial derivative of our answer and equate our phi of y to our g. So let's go ahead and do that. What I'm going to do now is I'm going to take partial derivative of y with respect to xy, but we know that's supposed to equal our g of xy. This is a fact. This is by definition that where f is equal to the gradient of phi. So if I take the partial derivative of my answer that I got by originally integrating my first coordinate function, if I take the partial derivative of that with respect to the second variable, what we end up with is x squared plus c prime of y on the left-hand side, and on the right-hand side we've got our x squared minus 3y squared. And so just to double check, make sure that makes sense, here was our phi of xy, and if I take the partial derivative of this with respect to y, this term right here vanishes because it doesn't depend on y. The derivative of x squared y with respect to y is just x squared, and the derivative of some unknown function, arbitrary function in terms of y, its derivative would be c prime of y. And so now we can make a positioning argument. We notice that the x squared terms, those depend on x's and y's, but the c prime of y must depend only on y, and so the terms inside of g of xy that depend only on y must be equivalent to our c prime of y. So we set these two equal to each other, giving us a new equation here. C prime of y is equal to minus 3y squared. So now what we can do is we can integrate c prime of y with respect to y. That would be the integral of minus 3y squared with respect to y. So that's going to give us c of y, and that's going to give us negative y cubed plus, and now I'm going to write c, and here I really do mean an arbitrary constant. Because it's not necessarily, it wouldn't be a function of x, because we already took care of all of our x components when we equated the components that depended upon both x and y to begin with, and we separated those from then the remaining components that depended just upon y and set that equal to our c prime of y. So at long last then we can say that our original phi of xy that this came from would be 3x plus x squared y. We knew all of that from our original integration step, and then we just found that the part of the expression that depends just on the variable y is this minus y cubed, and then if you want to think of it this way, we just tack on an arbitrary constant, sort of the way you always did in Calc 1 when you were taking a generic antiderivative. I think it's probably important that you check your answer. Check this. Does phi of x equal f? And does phi of y equal g? And the answer is yes. But it's very easy to check these, so I highly encourage you to do that after you do this complicated procedure. Okay, so folks, that was a little bit tricky. I'm going to let you try it in the problem below. I've given you some vector field, and I want you to first verify that it's conservative. That's just some more practice with that. But then I want you to find the phi that would be the potential function to generate the vector field f. So go ahead and give that a shot. I'm not going to give you the answer to that, or I'm not going to give you the solution to that, but I am giving you the answer. You should find that phi of xy is equal to this expression here. So go ahead and do the work and see if you can make that true. Let me know if you have any questions on this, and this was the last video for our section 17.3 pre-work.